In 1940, in Tacoma, Washington, the Tacoma Narrow Bridge was completed. It was a remarkable achievement of engineering at the time. A suspension bridge stretching approximately 853 meters in total length, making it the third longest suspension bridge in the world when it opened. It costs about $6.4 million to build, an enormous investment at the time. And it stood as a proof of modern structural engineering. It worked successfully for 4 months after opening to the public. But on November 17, 1940, something unexpected happened.
These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge.
Under steady wind conditions, the bridge began to oscillate. At first, the movement was small. Then the oscillation increased. The amplitude grew larger and larger. The deck began twisting in torsion, one side rising while the other fell. The oscillation fed into itself, building energy with each cycle. Eventually, the motion became so violent that the structure failed catastrophically. What makes this event so important is that the bridge had been studied. The stresses were calculated, the trusses were designed, the cables were sized correctly. The design was efficient. From a traditional engineering perspective, it has satisfied the equations. But the failure did not come from static loading, it came from interaction with the air. The engineers did not fully account for the dynamic interaction between air and structure. The wind did not simply push on the bridge, it coupled with its motion. As the bridge moved, it altered the airflow, and as the airflow changed, it fed more energy back into the motion. This feedback loop amplified the oscillation until collapse occurred. Now here's the deeper issue. Even if the engineers at the time had decided to fully account for the aerodynamic forces, solving that problem analytically with simple straight equations would have been nearly impossible. The geometry of the bridge was complex, the airflow is governed by nonlinear partial differential equations. The structure motion was dynamic. To truly study the interaction, they would have needed to solve a coupled fluid structure problem in 3 dimensions. Something far beyond the analytical tools available in 1940. It was not just a lack of awareness, it was a lack of computational capability. Many engineering failures and many engineering successes depend on our ability to model systems too complex to solve by hand. So how did we move from unsolvable equations to the ability to simulate complex structures before building them? To answer that, we need to go back to the origins of computational modeling and the birth of numerical simulation. Long before engineers were simulating bridges and airflow, mathematicians were struggling with something deeper: partial differential equations. Equations that describe how heat flows through a material, how a beam bends under load, how fluids move, how structures deform. In theory, these equations are known. The governing physics had already been written down. Equations like the heat equation, the wave equation, the elasticity equations. But knowing the equation is not as easy as solving it. For simple shapes, a straight beam, a perfect plate, a uniform rod, mathematicians could derive closed-form solutions. These solutions were elegant, exact, and beautiful. But the real world is not simple. Real structures have irregular geometry, materials are not perfectly uniform, boundary conditions are complicated, loads change with time. And the moment geometry becomes complex, analytical solutions disappear. In the 1940s and 1950s, engineers began to think differently. Instead of trying to solve one enormous continuous equation over an entire structure, what if we broke this structure into smaller pieces? What if a complicated geometry could be divided into many tiny simple parts? Each small part could be described by a simple equation, each small part could be solved approximately, and then by assembling all of these small solutions together we could approximate the behavior of the entire structure. So they developed what we now call the Finite Element Method. To understand this, let's take an example. Imagine a simple bar or a spring like this one. You apply a force, and the spring elongates. If you increase the force, the displacement increases. This is one of the most basic mechanical phenomena we know. For a simple bar or spring under axial loading, the governing equation is very simple. It comes from equilibrium and material behavior. And it can be written as an ordinary equation, F equals Ku. If you know the stiffness of the bar, that is its strength, K, and you apply force F, you can directly compute the displacement, U. Now that we understand the governing equation, let's use it to build a computational model. Imagine that this bar has two ends, two nodes, node 1 on the left and node 2 on the right. The bar connects these two nodes. When the bar stretches, both nodes can move and forces act on both ends. We now want to apply the same physical law, F equals Ku, but at the nodal level. For this single bar element, the force displacement relations at the two ends can be written as this. The force at one node depends on the relative displacement between the two nodes. Now, here's the important step. Instead of keeping these equations separate, we assemble them into a matrix form, a form that computers love. Now let's complicate the problem. Imagine that the bar is no longer uniform, and instead it consists of two parts, each one with a different stiffness or material property. Because of that, we can no longer use a single equation for the entire bar. We now have two elements and three nodes, each element still governed by the same local law. Now we assemble two local equations together by the shared node. When we do that, we obtain a single global equation for the entire bar. In this equation, this matrix is called the stiffness matrix, also symbolized by K. And this is the displacement vector of all the nodes. And this is the force vector applied at the nodes. A simple computational problem is that you know the material, and you know the forces applied, and you want to compute the displacements at the nodes. This is the key idea behind numerical modeling. We start with the governing physical law, we apply it locally to small elements, then we assemble all local equations into one global system. This global system is what the computer solves. And this, at its core, is what almost all modern numerical simulations are doing today. Whether a structural, heat equation, fluids, or electromagnetics, the philosophy is the same: local equation assembled into a global system. Of course, real simulations are more complex than that. They involve higher dimensions, non-linear material, time dependence, and coupled physics. But the foundation is what we just did. In the next video, we're gonna talk about the famous simulation softwares out there. If you enjoyed this way of explaining things, focusing on the mathematics and reasoning behind simulation, I'd really like to hear your thoughts. If you want to support this project and follow along as it grows, you'll find the links below. Thank you for watching, and welcome to Engineering the Invisible.